So one really powerful thing about the integral is that the idea and the notion of the integral being the area under the curve has a lot of implications in physics and other applications. So we're just going to be getting a flavor of some of those applications and doing problems related to it. And I'm going to call this integral as net change. And so let's just get right into it. It's just going to be mostly an application-based video. So the first one is velocity and displacement. So we know that like velocity times time will give you displacement, and we can then given that idea, um, we know that like velocity is given by the like this is velocity and it's like ds over dt. And if we multiply by time, we're essentially finding the area under the velocity curve, and that will give us displacement. And so there's that relationship between velocity and displacement of how the area under the velocity curve gives us displacement is very important when it comes to integrals, because we can utilize integrals to find the displacement of arbitrary velocity graphs. So we're given that ds over dt, for example, is equal to t squared minus 8 divided by t plus 1 squared. And we want to find displacement from t is equal to 0 to t is equal to 5. So this is a very this just means, since we know that displacement is simply the area under the curve of the velocity graph, and we're now just told the bounds from 0 to 5, that means we just have to evaluate the definite integral from 0 to 5 of this ds over dt graph, which is also the velocity curve. So the problem just becomes evaluating this. So if you notice, the hardest part is coming up with the integral we have to solve, and then solving the integral just becomes pretty mechanical. And so let's now solve the integral. This is t cubed divided by 3, t plus 1 to the negative 2. So if you add 1, that's negative 1. So that will be 8 over, well, plus 8 since minus, times minus 1, plus 8 divided by t plus 1. And we're evaluating this from 0 to 5. And so that ends up becoming 125 divided by 3 plus 8 divided by 6. And then we subtract that from 1/3 plus 8. So that just becomes 124 divided by 3 plus 4 over 3 minus 24 over 3. So that just becomes 104 divided by 3. And therefore that will be our displacement. So quite simple what we're trying to do. We're just trying to find the right integral to evaluate, and then using the idea, and we have to figure out the right integral by kind of noticing that the integral is the area under the curve. And once we have that relationship, we just simply have to evaluate the integral correctly. So let's do another problem. This problem, I'm going to call it problem 2. It states that rate of consumption of food is C of t is equal to 2.2 plus 1.1 to the t, where t is the year. T is since 1970. So t equals 0, I assume, is 1970. Find consumption between 1972 and 1973. So the idea is this consumption graph gives us how much food is consumed at a particular time t, and it's continuous, right? And we want to find the total consumption. So let's just say we have an arbitrary consumption graph, right? And I mean, this is an exponential, so I can at least try to like relate it by an exponential. And we're given like this represents particular time, how much food's eaten. But we want to find out the food eaten in an entire interval between 1972 and 3. So you can kind of think of that interval as like this entire part. And if we add up all of those parts, we get the total number of food eaten. So we're trying to find the integral in this interval of 1972 and 1973. And I think this is between beginning of 1972 and end of 1973. And end of 1973 means like the beginning of 1974. And since 1970 equals 0, that means beginning of 1972 is simply t is equal to 2, and end of 1973, also the beginning of 1974, is simply t is equal to 4. So that's our bounds. So we know our bounds is from 2 to 4. And then our equation is 2.2 plus 1.1 to the power of t dt. And we're just solving for this integral. The left side is just 2.2t. And then 1.1 to the power of t, we'll get 1.1 to the power of t over here. And then we have to divide by the natural log of 1.1. That's our integral. And we're evaluating that between t equals 2 and t equals 4. So that will just be 2.2 times 4 plus 1.1 to the power of 4 divided by natural log of 1.1 minus 2.2 to the times 2 plus 1.1 to the power of 2 divided by natural log of 1.1. And if I were to simplify a bit, this just becomes 4.4 plus 1.1 to the power of 4 minus 1.1 to the power of 2, all divided by the natural log of 1.1. And that's the total amount of food consumed between those 2 years. Again, notice how like the hardest part was noticing that we had to find the integral given all this information. And once we did that, the rest of it is pretty mechanical since we've done a lot of work with integrals. Let's do one final physics example. And for those of you not familiar with physics, I'll just tell you that work done is a concept in physics, and that's the same thing as the area under the force curve. And so it's kind of unfortunate, like if you are not very familiar with physics, because a lot of applications of integrals come from physics, and it's kind of hard to find real life applications that are not physics related. So hopefully you guys can just cope with this information I'm giving. So yeah, work done is the area under the force curve. We're told that it takes 10 newtons of force to stretch a spring 2 meters. Given that, how much work to stretch from 0 to 4 meters? And whenever we stretch a spring, there's a law called the Hooke's law. That governs that the force to stretch a spring from its natural length is governed by the force is equal to k times x, where x is how much you're stretching it from its natural position. And we're told that it takes 10 newtons to stretch it 2 meters, so we can solve for k. So k is equal to, 10 is equal to k times 2, and therefore k is equal to 5. So now we know that force is equal to 5 times x. So we have the equation for our work or force. And I told you that work done is the area under the force curve. So to find the work done to stretch from 0 to 4 meters, we just have to find the area under the force curve in that interval. So we're just solving for this integral. and that is simply phi over 2 x squared from 0 to 4. So that is phi over 2 times 16, which is equal to 40 Newton meters. So yeah, I mean, a lot of this had to do with like physics knowledge. So I would not blame you if you're confused, if you're not familiar with physics, but a lot of applications of integrals, especially viewing it as the net change, comes from physics. But hopefully this gave you some intuition of how powerful integrals can be to solve applications.